All right, so we're going to go ahead and talk about sound today, and we've already talked quite a bit about waves, so we're going to go ahead and roll straight on. Let's talk about what sound is. So there's transverse waves and there is longitudinal waves. Transverse waves where the motion is perpendicular to the wave motion, and longitudinal waves where the particle motion is parallel to the wave motion. So sound is a type of longitudinal wave. It is also known as a compression wave because it works off of actual compressions of molecules, one hitting another, kind of like that example of the slinky where if I push it, one chain will hit the next, hit the next, hit the next. Except obviously sound works out in all three dimensions of space, so please consider that. So one key thing is that sound does need a medium. It needs stuff through which to travel, okay, a medium. Light obviously can travel through a vacuum, right? Does not need a medium, it just needs space itself. So if you look out at the sun, obviously the light from the sun is getting to you, and therefore it does not actually need a medium. And so sound cannot travel through a vacuum. Whenever you watch those movies, the awesome, Star Wars movies, whatever it might be, and, the explosion in space and the whole theater rumbles, it sure looks cool, but you know what? It's not going to happen. If you are in a spaceship and your spaceship starts to rumble because there's an explosion nearby, that's a problem because that means that stuff is hitting the hull of your ship, and you're not going to survive that one. So sound does not travel in space, and so my objective, of course, is to ruin all future movies for you. I'll do whatever I can to do that. Let's look at the speed of sound. So first off, let me address this very common misconception. The only thing that affects the speed of sound is the medium through which it travels. That's basically true of all waves, whether it be light or sound or any other type of wave. What determines the speed of the wave is what the wave is and the material through which it's traveling. So, for example, when dealing with sound travels through the air at a speed based on the air. That's going to be the air temperature, the air material, the air density, humidity. All those things are factors because that's change in the material itself, that is the air. Those are the only things that are going to affect the speed of sound. So a very common misconception is to think that frequency or amplitude would change the speed. It does not. Think about this. The sound that's coming from my voice right now, I can change the frequency. I can talk a little bit lower like Barry White, or I can talk really high voice like Mickey Mouse. And in either case, it does not change the speed of sound. I'll give you a moment to get over my awesome impression of Mickey Mouse there. What about amplitude? It's a pretty common misconception to think that if I talk louder, it somehow is changing the speed of sound. It does not, right? The volume of my voice is the amplitude of the wave. That is how high the crest is or peak, how low the trough is. So by increasing the volume, I'm effectively increasing the amplitude and making the crests or peaks higher and the troughs lower. So what changes the speed of sound? It is material through which it travels. And here's a few common speeds of sound through different materials. So in the air of the room that you are in right now, it's about 343 meters per second. You don't need to memorize these typically, but that top one is probably a pretty good one to kind of know. You know how it is. Most of these speeds are going to be, things that would be given to you, and that typically would be the case even with the speed of sound in air. You don't need to memorize it, but it's something that comes in handy if you have that knowledge in your back pocket, So 343 meters per second is the speed of sound at room temperature and at 1 atm, meaning at typical atmospheric pressures. At 0 degrees Celsius, it's about 330, 331 meters per second at freezing temperatures. If you notice, these other materials like helium and hydrogen, they have faster speeds of sound. These are very lightweight gas molecules where it doesn't take much energy to move from one molecule to the other, just transferring that energy through. With solids and liquids, since they're non-compressible materials, typically, the more dense the material, typically the faster the speed of sound. So let's look at iron and steel. It has a very, very high speed of sound, which is why in old Western movies, you always see someone like, whenever there's an old Western, and I'm sure you guys are really into the old Westerns, whenever there's an old Western, you might like see someone putting their ear to like the train tracks. And the reason why they would do that in those movies is because that actually is a reasonable thing to do, to be able to hear the train coming, because the sound travels very well through that dense solid material, and it travels very fast. You would be able to hear any sort of event through the steel before you heard it through the air. So kind of a crazy, weird example is that what if like the train going down the tracks blows up? The person who has his ear to the tracks would hear that explosion through the tracks before anybody who's just like standing out in the air, right? He would hear it much sooner, actually. So it isn't just that it travels faster and better, or it isn't just that it travels for a longer distance, but also that it travels faster. Okay, so let's go ahead and move right along. I'm going to wind up skipping some of these slides, but let's just kind of go ahead and move along. Okay, so we have the audible range is from 20 hertz to 20,000 hertz. That is our human ability to hear sounds. So the frequency above that 20,000 hertz, I think most people can kind of understand reasonably that, okay, the vibrations are so fast that I can't hear it. I think people have a hard time understanding this concept that below some sort of vibrational frequency, you couldn't hear it. And in fact, there's times when I can actually make a speaker diaphragm vibrate at a rate that is slower than 20 hertz. You can see it moving back and forth, but you can't hear it, and it's frankly a little bit creepy to see. So why is it that we have this range? And that's something that I'll talk about a little bit here. So to do that, let me talk about the structure of the ear a little bit. You obviously have your earlobe, you have your ear canal, which is basically the hole that you stick your finger in when you go clean out your ears, right? So that's your auditory canal. And then you have your eardrum, okay? So it's basically a diaphragm, very similar to a speaker diaphragm, to be quite honest. And on the other side of that diaphragm is what basically is a fluid. And so you have the inner ear. And then actually on the other side of the eardrum, you actually have three bones. You have the hammer, anvil, and stirrup. And then on the other side of that, you have the that fluid. And so then you have the cochlea in there, where there is these hair-like fibers that will pick up the sound vibrations. And so those hair-like fibers will vibrate, and it sends a signal into the auditory nerve. Your eardrum is going to be pretty similar to a speaker, kind of like my speaker here, right? So it's just a diaphragm that moves back and forth, okay? And so that movement back and forth is basically just it's as simple as that. That's how sound is produced. So why is it that we have this hearing range between 20 and 20,000 hertz? Well, these hair-like fibers that need to pick up those signals and send them to your auditory nerve, every object has some sort of resonant frequency. So if you think about it, in order to pick up a very high frequency sound and send the signal to your auditory nerve, these hair-like fibers need to be able to vibrate back and forth and then send that signal. In order for the hair-like fiber, right, if you think about it, the longer the hair, I'm gonna make this selfie stick like my finger, right? This is the hair. The longer the object, the longer it's gonna take for it to go back and forth. If it's a really small object, it has the ability to go back and forth more quickly and easily, right? So these different hair fibers are able to vibrate at certain frequencies and pick up the sounds. And so if you think about it, the vibration is happening so quickly, it could happen so quickly that this hair doesn't even get a chance to vibrate with it, right? The vibrations trying to get this thing to go back and forth are happening, right? If I were to move my finger from an external source, okay, I can get it to move back and forth. However, if this vibration is happening so fast, this thing is effectively just standing still because the outside vibration is so fast, this thing can't even pick it up. The same is sort of true in terms of the long vibrations, in that frequencies below 20 hertz is not going to cause those hairs to even wind up sending a signal to that auditory nerve. So that's essentially the idea there. That is fundamental to our hearing. Most people know that dogs have the ability to hear frequencies over 20,000 hertz. I think, if I'm not mistaken, their high end is somewhere around 40,000 hertz. And also something to keep in mind, that this number between 20 and 20,000 hertz is a generic number that is basically for children. As you get older, your ability to hear decreases over time, especially the high end. So for those of you here, it is unlikely that you would be able to actually hear at 20,000 hertz, or for even 19,000 hertz for that matter. If I were to be a betting man, I would say that on average you guys can probably hear somewhere around 17,500 hertz or so on the high end. And you know what? Let's test it. So I'm going to go ahead and do that in a minute. But I want to talk a little bit about what sound is, again, and just to kind of think about what's happening there. So the sound that's coming from my voice is happening because I have vocal cords that are vibrating back and forth at a certain frequency in order to cause these sounds. If I talk like Mickey Mouse again, right? In order to do that, those vocal cords are going to vibrate back and forth more quickly, right? That's a higher frequency. That is the frequency with which the vocal cords go back and forth. That is the frequency of the sound. In order to duplicate that sound, again, I can have my speaker here, and all the speaker needs to do is go back and forth. Okay, it's going to compress and it's going to pull back. It's going to go forward and it's going to come back. And all it needs to do is go back and forth at that same rate in order to reproduce the sound of my voice, which is how you're hearing me in your speakers. So what is sound? It's known as a compression wave, a longitudinal compression wave, but why is it called a compression wave? Because it's made up of these compressions and rarefractions. So the diaphragm of the speaker compresses, right? It moves forward. The diaphragm moves forward towards you. So it makes a compression wave going towards you. And it's a compression that propagates through space. To get you to visualize that, I want you to try and think about this toy that I have. It's basically made of effectively, it's like a small garbage can with a hole cut on it, and like a piece of plastic and an elastic band on it. So basically what you do is, I'm trying to think, just basically it's a hollow tube you can do it with any sort of hollow tube, put a piece of plastic and some elastic on it. You can snap back the elastic and it will create a compression. And so it's known as an Airzooka, if you want to actually know what that toy is. They're fun to play with on Amazon. Go buy one. So what you can do is you can basically snap this thing back. It's going to compress with the plastic. It's going to push the air forward, and because of the sort of tube structure, it isolates that compression of air and pushes it towards you. And it's kind of a fun toy to play with, because you can actually create this compression of air that you can't see, but I could be 40 feet away from you and I snap that thing back and that compression of air comes and hits you. And when I first do it, snap it, there's a delay because it takes time for that compression to get to you. So at first people often think, oh, what happened? And then all of a sudden, people with long hair, their hair kind of gets pushed back and it's kind of fun. So if you can visualize that at all, it's sort of like that compression that's coming towards you. Sound is a very similar idea. Not exactly the same, but it's the same sort of general idea. So when the speaker moves back and forth, what's happening? So in a compression, the diaphragm moves towards you. Okay, it creates a compression, and that compression moves towards you. But then what does the speaker do? It then retracts back, and it actually makes what's known as a refraction. So when the speaker moves towards you, it's actually compressing the air molecules. Okay, it's compressing them, and that higher air pressure propagates through space. When it pulls back, it is reducing the air pressure. The air pressure is going to be less in that space, so less pressure is rarefied air. Just like when you have a steak cooked that is less done, it is rare, right? It's cooked rare. So rarefied air is air with less pressure. So that's all a speaker does, is it compresses and it rarefies. It compresses and rarefies. And so those propagations will go through space and then until they get to your ear, causing your ear to vibrate back and forth at that same frequency and causing sound. So let's try and do a little bit of a hearing test. And I'm going to go ahead and just look up, if you just do a Google search for frequency generator, and usually the top one here, this is, I found to be a really good one. And what I'd like to do is actually start really high, so it starts as high as a little over 20,000 hertz. I'm going to sweep down. I suppose that what we can do to make it go a little bit faster is to go from in 500 increments, 500 hertz increments. And so let's start with a let's just start with a, let's say 1000 hertz sound, just to make sure that you are able to hear this sound. Let's give it a go. Okay, so you are trying to listen to just a very generic sort of tone. I'll make sure that the volume is cranked up on this guy. All right, so you should be hearing a sound just to kind of give you the feel of what a different sound is like, right? Okay, so you're going to be hearing a very, very high frequency sound. You are not going to like it. That's not the objective here. The objective is to annoy the heck out of you. That is my job. All right, so I'm going to start with the sound. Here you go. Ready? Can anybody hear it? I didn't think so. Okay, so here's what we're going to do. We're going to start essentially at 20,000 hertz. That's where it is now. The sound is being produced, by the way. If anybody has dogs, look at them right now. See if they're reacting. All right, so let's go ahead and go to 19,500 hertz, and let's see if anybody can hear that. If you can hear it, those that are live with me right now, you can throw it in the chat. Just say, type in the number that you were able to hear at. So here we go, 19,500. 19,000. 18,500. Here we go. 18,000. 17.5. I have a feeling that this one might hit a few people. Once you can hear it, you can go ahead and kind of ignore me from there. That's got my left ear, so I can actually hear better out of my left ear than I can my right. All right, I'm going to stop it there. I'm going to assume that those of you who couldn't hear it, it was more just of an issue of the sound and not actually getting across through my system to you properly. I would really like it if you guys are able to actually do it on your own for a minute, just because I want to see where your hearing is. So I'm actually going to give you guys an opportunity to do that right now, and let's see how that works out. So hopefully you guys were able to demonstrate that you have some good hearing. And I'll actually express my own personal issue with my hearing here in a moment. Let's look at intensity for a moment. And in fact, yep, okay. So, and I'll get, when I get to the parts of the ear, I'll talk about my own issue a little bit. So intensity is basically power per cross-sectional area. So the cross-sectional area that comes towards you, how much energy per second is in that cross-sectional area. And so that deals directly with the amount of energy there is. So intensity is something that increases exponentially or decreases exponentially with distance, and I'll get to that in a moment. But you'll notice the intensity and sound level are a little bit different. So decibels is our perception of sound. Our perception of sound works a little bit more along the lines of like a linear progression in terms of distance. If you're twice as far, you're going to be able to hear about 2 times as less. That's a bit more on how our hearing works versus intensity, the actual amount of energy that's getting to you. It's an inverse square law issue. So if you are twice as far, the amount of power that's getting to you is 4 times less. If you're 3 times as far, it's 9 times less energy. So here's the sound level measured in decibels for various things. So, a typical talk, somebody who's fairly close to you would be 65 decibels. A loud rock concert, 120 decibels. A jet plane at 140. So hearing damage happens somewhere around the 100, 120 decibel range. That's where it kind of starts to become damaging, especially right around that 120. So that can start to cause some permanent damage, so try and stay away from those louder sounds, wear earplugs, that kind of thing. So what are decibels? So this is how you determine the number of decibels of a sound. So decibels is this beta symbol. Measured in decibels, it is 10 times the log of I over I naught. So what is I and I naught? So I is the intensity, the power per square meter. It is the intensity of the sound that you're hearing. That is divided by the slightest sound you have the ability to hear. That is known as the threshold of hearing. And it is a generic value that we kind of give for all people. So basically, on average, the average person can hear at the very slightest volume, they can hear an intensity of this level. So the measurement in decibels is a logarithmic scale that kind of goes in line with what our perception is, as opposed to intensity is, as I said, it goes to the inverse square law. So it is proportional, right? This is the proportional to symbol. So the intensity is proportional to the inverse of the square, meaning, again, as I said, as you double your distance, your intensity, or the energy getting to you per second, would be 4 times less. Okay, so let's talk about the parts of the ear. So I've already talked about this a little bit. The eardrum, the hammer, anvil, and stirrup are the 3 bones that are in there, and then that transmits signal through the semicircular canals and your cochlea. And then obviously eventually to the auditory nerve. So with me, I remember the day pretty well. I had a really bad cold when I was 17, and I went into my dad's shop to help him out with some construction stuff, and working on some metal. I just heard a loud pop, and all of a sudden I could feel something loose in my ear. And I've gone to specialists, and they won't do surgery because my hearing is still pretty much fine. However, louder sounds cause me to have some serious discomfort. So I can literally, like any sounds probably above about 100 to 120 decibels, it will actually cause one of those bones in my ear that they think is broken to rattle around. I can feel it rattling around in my ear. Sometimes my own voice does it. So I know my own voice doesn't just annoy you sometimes. It also annoys me. So especially when I have a cold, for whatever reason, it seems to break it free. And my own voice, I will be teaching sometimes. And the very fact that I'm talking, the vibration will cause that thing to vibrate. And it's all I can think about. So here I am trying to like talk about something technical, and I'm just being distracted by the loose thing that's in my head. I'm not even talking about my brain this time. No, I hate pep rallies. Hate. So that's why I don't go to concerts, and it's why when I ride my motorcycle, I usually wear earplugs. You should anyway, but basically almost every single time if I'm on the freeway on my motorcycle, I will have that happening in my ear. So here's something pretty interesting with the function of the ear is sometimes there will be some sort of damage to one of the bones, like what I have, and so someone can still hear sounds. Here's how you can kind of navigate around that, is you can bypass this part of the system altogether. You can bypass the outer ear. What you can do is you can instead, in fact, in my classroom I have these headphones that I bought for like $40 just as a demonstration device, where the headphones they go behind your head and press up against your skull. The headphones don't go in your ears at all. Not on your ears at all. They just press up against your skull. And the vibrations vibrate your skull, and those vibrations will channel, bypassing the eardrum completely, and actually allow those sounds to vibrate inside of the cochlea and cause that those sounds to actually kind of go more directly to the auditory nerve. So it's really interesting. I just out of curiosity, my dad, before he had hearing aids, I gave those headphones to him to try out, and he was able to like hear really well with them because I was actually able to put a mic to it, so that way he could hear things. Pretty interesting. All right, so here what I've made is I've made an ear canal. So that's your auditory canal. Your auditory canal is just like from that picture that I had been showing you. It is literally just a tube with a closed end and an open end, right? The closed end is where the eardrum is, and the open end is, well, you know, the hole that you stick your finger in. Don't do that. By the way, don't use Q-tips to clean your ears. It's really, you're not supposed to. Most people actually wind up causing damage to their eardrum because they go in too far, and it's not what ear, nose, and throat specialists suggest. Hey, what do you know? The more you know. So let me kind of get back to this whole thing. So here is that auditory canal. There are 3 resonant frequencies inside of the auditory canal. Every object has its own resonant frequency. So at least kind of within reason. So some objects will resonate better than others. Obviously, you guys know that like taking like a crystal glass, a really nice crystal glass, wet your finger and you can rub across the top and you can get it to resonate and make a sound, right? So some objects have better resonant frequencies than others. My speaker on my desktop here, right? This speaker, the box itself has a resonant frequency to it. The size of this box by the acoustic engineers that developed this speaker, they did not choose this box necessarily randomly. It is very likely that they chose the size of this box very specifically in order to help amplify certain sounds that this speaker is meant to drive out. So for like a drum set, for example, an acoustic engineer who is developing a speaker for a PA system often will make the box such a size where the box itself has a resonant frequency that matches up with the drum that is hit the most often. So that way the speaker driver, the diaphragm, doesn't have to put out so much energy in order to really amplify that specific sound, because that's the sound that's being produced the most often. So this, for example, has a resonant frequency, right? It resonates after I hit it pretty nicely, right? Just a cup, right? And so if I hit it and then hold it, what's happening there when I do that? So the cup itself is actually resonating. It's vibrating back and forth. There are nodes and antinodes being developed on the object. In fact, the spot where I touch it clearly that must be where at least it's definitely not a node there. Notice how I can hold it from the bottom, and I'm not going to disrupt that sound. So I must be holding it from some sort of nodal area. That must be an antinodal area where I can easily disrupt the sound. So let's take a look at what happens inside of the auditory canal. There are 3 resonant frequencies that happen inside of the ear. So let's go ahead and draw that out. Let's say that we have a sound that goes inside of your ear, okay? And it's going to, because it's an open tube, it's going to have an antinode at the open end. Let me go ahead and dot line make the rest of this wave. Okay, and then I'm going to also make the reflection. I'll put that in a different color. So here's the reflected wave, antinode at the open end and a node at the closed end. And then the reflected wave will continue something like this. If I can make it continue. Okay, so the entire wave is continuing out and you hear this sound, but at certain frequencies, you get a perfect resonant frequency where the nodes and antinodes are staying in the same spot, and that sound would be particularly loud for you. So what frequency would that be? Well, it turns out that the distance between here and here is about 1 inch. Okay, that's 1 inch. 1 inch is the same thing as 2.54 centimeters, right? That's 2.54 centimeters. And let's see, that means that it would be equal to 0.0254 meters. Probably not that precise because my 1 inch is pretty well rounded off, so it's clearly not that precise of a number, but forgive me. So let's figure out what the wavelength would be for this sound. So please think about this as I go about it. If the auditory canal has a length that is 0.0, in fact, let's think of it in inches for a second, then we'll do our simple conversion. If the auditory canal is inches, 1 inch, okay, it is 1 inch of the auditory canal. Think and look at the picture here. How much of the wave is actually in the auditory canal? How much of the wave is actually in the tube? And then think to yourself, how long is the entire wave? How long is the entire... So if the auditory canal is 1 inch, how long is the entire wave? What is the length of one wavelength? Think about that. Yeah, so we have that if 1/4 of the wave is in the tube, then the entire wave must be 4 times the length of that tube. So essentially, if I know that 1/4 of the wave is in the tube, then I'm going to multiply the tube length by the reciprocal. Okay, I would multiply it by 4/1, which is the same thing as 4. You could also have a scenario where if I, you know what, let me continue on this problem, and then I'll give you my alternate scenario. So that means that it would be 4 inches, or it would be approximately, in this case, it would be 0.1 meters. That is the wavelength. Okay, so the wavelength is equal to that 0.1 meters. And so the velocity is equal to wavelength times frequency. And so we know what the speed of sound is, that at room temperature is equal to 343 meters per second. And I know that the wavelength is 0.1 meters. So 343 divided by 0.1 would be 3,430 hertz, or cycles per second. So what if we were to set up our frequency generator to that specific sound, to 3,430 hertz? I'm not going to play it for very long. That sound, or at least something close to it, is a sound that should be particularly, well, annoying to you. Each person has a different length to their auditory canal. Okay, so for some of you, it might not be so annoying. But I promise you that if I were to do that sound and then sweep around it for a little bit, right? And go a little bit higher, a little bit lower. At some point, it's just going to suddenly start to sound really loud. And you're going to be like, oh God, make it stop, right? And so there are 3 different frequencies that are within our auditory range that are resonant frequencies. The next one, right, that was the fundamental that we just demonstrated. The next one, if I can erase this part, this is that alternate scenario I was talking about. The next one would look like this, where it would be an antinode at the open end, but there would be another antinode inside of the canal. So I'm just going to kind of continue that a little bit, and let's do the reflected part of the wave, right? So the reflected part looks something like this. I know it's not perfect, but you'll have to forgive me a little bit. So in this case, how much of the wave is in the tube? Well, 3/4 of the wave is in the tube. So what I would do is I would take the length of the tube, which again is still 1 inch, and I would multiply it by the reciprocal of this. So I'd multiply it by 4/3 to figure out how long the wavelength is. Okay, so it'd be 1 1/3 inches long of a wavelength. And I could then figure out what frequency the next one would be. I would take 4/3 time, let's see, I would take 3 divided by the 1.33, and that would give me that next frequency. Okay, so that's a pretty good, frankly, to be honest, that's a pretty typical sort of application to this sort of content. What's often done is an experiment where we adjust the length of a tube with a tuning fork. We put a sound in until we hear resonance, and then we can determine, using this equation, we can determine the speed of sound. It's actually a pretty accurate way to do it. All right, so let me go ahead and talk about something else that's pretty interesting about this speaker structure that I've talked about a couple of times. So when I first started talking about this, I was talking about how, sorry, I'm just going to move things around. I'm going to talk about how the speaker, when it makes sound, it makes a compression of this diaphragm and then makes a refraction. Okay, but think about this. Every single time that it pushes forward and makes a compression, what's happening on the back side of the speaker? Right? If I was behind the speaker, what if there was no box? On the back side of the speaker, for you there's a compression, but for me there's a rarefaction, isn't there? That rarefaction propagates through space in the same sort of way. So there's not only sound being produced in front of the speaker, there's also sound being produced on the back side, which is why there's always a hole, okay, in a speaker. Sound will come out of this as well. Bose very famously had started to take advantage of this fact. And so some years ago, back in the late 80s, they started to make these speakers that would take the sound from the back end of the speaker and they would channel it through these series of channels of various sizes. And the channels had resonant frequencies that they were purposely made so that way it would resonate the longer wavelength frequencies. And so they would channel the sound out through the front. So this speaker has a hole in the back, but those Bose speakers would channel the sound and put a hole in the front. And through that hole, you would be getting the sound from the back end of the speaker. However, it would be purposely magnifying the deeper tones of that back end of the speaker. So that way the speaker could have better bass without having to have a big giant subwoofer. And so that's something that's been pretty big behind Bose's technology. That's why the company got so big in the first place, was that fairly ingenuitive design. Okay, so we've talked a little about resonant frequencies. We've talked about some interference. Okay, so we've talked about interference in the past especially. So let's look at interference patterns in a 2D world. So remember interference, constructive interference, where a crest and a crest meet and it makes a bigger wave. Destructive interference, where a crest and a trough meet and it makes a smaller wave. But how does that actually relate to the real world? So this would be like 2 speakers. Let me actually separate these 2 things out. Oop, that didn't work. Let me, okay, try this again. Okay, so I have these two speakers, and you're like, these are just a bunch of circles. So these two speakers are making sound, and they're making sound at the same frequency, hence these being the wavefronts of each sound. Okay, so here you are somewhere in between, and the sound from this speaker is going to get to you, and the sound from this speaker is going to get to you. If you are somewhere right in between, you are getting sound from both sides, and you have the wave crest getting to you at the same time. The sound would sound twice as loud because it's coming to you from both speakers. However, I want you to pay close attention to what's happening as I bring the two speakers closer together. There is a reason why you should have your main speakers at separate corners of your room, or at least separate corners of your desk, and do not put the two close together. Never put your speakers close together. Watch what happens. You can see visually what happens. Let me start by bringing that one in close. Okay, so watch what happens with these patterns. Do you see these lines developing? A little bit psychedelic to watch, actually. It's especially here that I want you to pay attention to. Whoa. Well, the two speakers obviously can't be over top of each other. So let's go to right about... let me purposely get to right here. Oh, that's going to be perfect. Okay. So we have these nodal and antinodal lines that develop. So let's see. Right here, along this path right here, we have a crest on top of a crest, a trough on top of a trough. So this red line and this one over here represent antinodal lines, where the crest and a crest are both at the same spot, so it's going to sound louder. Trough and a trough, again, they add together. However, let's see, where else is there an antinodal line? That would be right here. Okay, right there, there's an antinodal line, and right there, there's an antinodal line. So if you're in these locations, if you're anywhere along these lines, the sound from these two speakers would sound very loud. However, let me change colors. What about here? And here, and here, and here. You see those spots, you have a crest from one wave in the trough of another. If you were anywhere within these purple sort of line areas, you would hear nothing. Like the person over here who's standing over in the red line area, they're jamming out. And here you are, and you hear nothing. You're like, what? Are you hearing voices? What are you talking about? I hear nothing. And so when you have two speakers together, there will be nodal and antinodal lines at specific frequencies. So keep in mind that this effect that I'm diagramming here happens at these specific positions only at this specific frequency. So those nodal and antinodal lines change depending on the frequency. The other issue is that even when I pull these two apart, let me see if I can get rid of all these lines that I made. Even when I pull these two speakers apart, the nodal and antinodal lines don't disappear necessarily. It's just that they become much, much smaller, so therefore less noticeable. You see, when the two speakers are so close together, and a nodal line can be in this room, right? If I were to actually put my two speakers right next to each other, and I step back and I listen to a certain sound, the nodal line, the area where there's destructive interference, can be so large, it can be larger than my head, which means I'm not going to hear the sound. However, when the speakers are far apart, the nodal lines are going to be so small, I'm not going to notice it, right? Because it's certainly smaller than the width of my head, so I'll be able to still hear the sound, and especially if it's so small of a nodal line that I won't even notice it within one ear. So there's a lot that goes into these concepts of acoustic engineering. It's really quite interesting when you start talking to someone about these concepts. Okay, let's kind of finish up with things here. There's a couple things I want to talk about still. You should know that not all sounds can be heard equally. So here's sort of a little chart that shows the different your ability to hear different frequencies. So right around that 4,000 hertz range, you actually cannot hear 4,000 hertz as well as you can hear other sounds, which is why sometimes some sounds sound worse than others, more annoying, if you will. We've talked about instruments. So when you have a stringed instrument, you have nodes and antinodes. You have a standing wave that's produced. And in fact, if I can even, I've talked about that stuff before, but let me show you, if I can, show you just a little something that's pretty awesome. There's some people who've done some pretty sweet videos on this. Let me see if I can. I know that I'll find it. If my internet will work. Yaha, this is the one I want. So you can actually see, I'll lower the volume on this. My internet. Really? Okay, there we go. So you guys can see the waves that are being produced here, right? Standing waves, and you can actually tell just by looking at it whether the instrument is in tune or out of tune, or if he doesn't have his finger on the fret correctly. So ideally the strings should have a standing wave where the nodes and antinodes aren't moving, but also you're going to have an issue of where the frame rate of the camera doesn't necessarily match the frame rate of the frequency of the string. But those waves are actually happening. Those standing waves are actually an occurrence in the string itself. So when I talked about this, the object itself does have nodes and antinodes. The structure itself has spots that are vibrating back and forth and other spots that are not. This is something that can be demonstrated that I'll do in my classroom where there are plates. I can take a metal plate and vibrate the whole metal plate and put salt on it. And the spots where it's vibrating, the salt will vibrate off. The spots that aren't vibrating, the salt will collect. And so you can actually see the nodes and antinodes. And I'll post some pictures of that. All right, so I've talked about this stuff a bit. And we've talked about beats, right? Beats are when you have different frequencies, and you have the beat frequency is going to be the difference in frequencies. So if I have a frequency of 50 hertz and a frequency of 49 hertz, then you're going to have a beat frequency of 1 hertz, where the sound is going to sound like it's getting louder and quieter, and it's going to do that 1 time per second. The thing I'd really like to get to here before we end is the Doppler effect. The Doppler effect is what happens when waves come towards you or away from you, and I think that we talked about that a little bit, but here is the equation that I want to get to right here. This equation, so our textbook has one equation for if it's coming towards you and one if it's going away from you. However, I prefer to just give this one equation that deals with all of it. So in the numerator, you're going to make it a plus instead of a negative, or a plus instead of a minus rather, if the observer is moving towards the source. In the denominator, you're going to make it a plus if the source is moving away from the observer. So the Doppler effect is that whole thing where a car comes by you, and when it is coming towards you, the frequency appears to be shifted to a higher frequency. When it's moving away from you, it seems to be shifted towards a lower frequency. Vroom, right? NASCAR going by you. Keep in mind, and super common misconception, keep in mind the speed of sound does not change, right? The speed of sound doesn't change, just your perceived frequency changes, okay? Because you're shortening the wavelength and expanding the wavelength, but the speed of sound is staying the same, okay? So here is an example problem. A source of 4 kilohertz or 4,000 hertz, sound travels at 1/9 the speed of sound toward a detector that's moving at 1/9 the speed of sound toward the source. What is the frequency, and how does the wavelength compare? Okay, so we have the sound. The source is going 1/9 the speed of sound towards the detector or observer, and then the observer is going 1/9 the speed of sound toward the source. So let's go ahead and look at our answer here. So the observer is moving towards the source, so we make the numerator a positive number. The source is moving towards the observer, so we make this a subtraction. And so going through the numbers, you would get a value of a perceived observed frequency of 5,000 hertz. Now, if you are changing the frequency by 5/4, right, you're increasing it by 5/4, then that means that you would have a shift of wavelength of 4/5. It would be the reciprocal. If you wind up actually going the speed of sound, you wind up getting this sort of conical, sort of shaped sonic boom, right? That get this shock wave. And I'm going to end things probably in terms of my discussion or my lecture on this. There's lots of videos of jets breaking the sound barrier. I'm trying to pick out the one that's best. This is the one I was looking at before. And I'm going to bring the volume down. So this is the part right here I want you to really look at. Okay, look at this. Do you see how there's like a cloud around this thing? So what happens is the jet will compress the air around it so much in that conical sort of shape that it actually literally squeezes the moisture out of the air because the air is compressed so very much. All right. So I think with that, I'm going to kind of end my long, drawn out sort of lecture on this topic.